How many ways can 3 A's and 6 B's be placed in a row if the A's are not next to each other? So for example, we can have an A, a B, an A, a B, an A. So in other words, all the A's are separated by B's. So we've used 2 of the B's. We still have 4 more. And there's one example of that scenario. So we have the A's and B's in a row, and each of the A's are not next to each other. Now if you think about it, I could have taken this last A here and moved it over one spot, or I could have moved it to that spot, or I could have moved it to that spot, or possibly put it in the last spot. So there's 1, 2, 3, 4, 5 places that last A could have been moved if I kept the first 2 A's in their same spots. Now, if we think about it, we could move both of those A's over. So there's 1, 2, 3, 4, 5, 6 B's, or 3 A's. And now move this A in here, and I notice there are 4 locations there. So notice I'm creating a pattern of a way of figuring this out. Now, this gets to be a little tedious, especially if there's a large number of A's and B's. And even with this, it's sort of tedious. So let's think about this for a second. We have our 6 B's. They're the ones we're really concerned about. And we have the locations that we can place the A's. So each red line represents a location where an A can be placed. Now all the B's are identical, so they're just in a row. We don't one way of doing that. But notice these red marks are the locations for where the A's are, and by our choice in our problem, when I start picking these locations, I can only place one A in that spot. In other words, I can't repeat that spot. Also, if I put A's in these first 3 locations, it doesn't matter if I start on the first, second, third spot, or if I go third, second, first spot. In other words, once I put an A in that spot, it's there. It doesn't matter the order of these things are placed in that spot. So what I decided here, and what I sort of talked through here, is that, well, you can't repeat locations. Using the first, second, and third location is just the same as using the third, first, and second location. So we have figured out that it's a combination. So how many locations are available for those A's? Well, there's 1, 2, 3, 4, 5, 6, 7 locations. 7 spots that are available. And how many of those spots do we need to have? Well, we have 3 A's. We need 3 of them. So to solve this problem, figure out how many different ways can I put 3 A's and 6 B's in a row. Well, combination 7 choose 3. In how many ways can 7 people be placed around a circular table? So let's give these people's names: A, B, C, D, F, and G. So here's my circular table, and I want to place them in this circle. So there is one order around this table. Now, the thing to remember is when we talk about placed around a circular table, we're not using any external reference. So if we think about this, there's one seating arrangement. Now if I had everybody get up and move over one seat, in other words, just rotating, have we changed the seating arrangement? Well, in that case the answer is no. Because just sitting up and rotating one seat over, you're still next to the same people that you've been to all along. So because of this, we have to do this count just slightly different. So we start off with a table, and we need to take one of the spots and in essence fix it. What this fixing does is it gets rid of the rotation. So let's just put person A at that location. Now the other people we have the other 6 chairs empty. We say, okay, well, let's put the other people in the spot. Well, this next seat, I have how many choices? I had 6 choices, and then 5 choices, 4 choices, 3, 2, and 1. So if you multiply that together, you see that that is 6 factorial. So for our problem, how many ways could 7 people be placed around a row? We had 6 factorial. Now if we do this in general, in other words, if we have n people, the formula for this is n minus 1 factorial. Sometimes you'll see written it as n factorial divided by n. It's the same thing. But basically, by coming with one less than the number of people, we're eliminating that rotation. In other words, everybody rotate one seat, rotate one seat. We don't want to count that as different. And we want to know how many shuttle crews can be formed using the requirements that are listed above. Now, the shuttle commander and pilot are to be chosen from a group of 8 candidates. Well, if you think about this, if John is the commander and Sue is the pilot, is that different than if Sue is the pilot, or Sue is the commander and John is the pilot? So the commander and pilot are necessary titles, so order is important there. So when we pick the commander and the pilot from that group of 8 people, it's a permutation. 8 choose 2. The 3 engineers are selected from 12 candidates. So from those 12 candidates, we're selecting 3 engineers. Now, are we concerned about titles to this? In other words, do we have a head engineer, assistant engineer, and the person that does all the work? Nope, they're just called engineers. So that tells me that it's a combination. So from those 12 people, we pick 3. The scientist is picked from 5 candidates. Now, if you're picking just one person, in other words, anything choose 1, whether it's a combination or permutation, is just the number of the choices you have. And the civilian from 2 candidates, so combination 2 choose 1. Next question. In how many ways can 4 couples be seated in a row of 8 seats at a theater if each couple is seated together? So there's our 8 seats. Now there's 2 ways to work this problem. The first method thinks about it as here's your 8 chairs. For the first chair we have 8 people that could be in that seat. Whoever's seated in that seat, the other part of the couple has to be in the next seat. So 8 times 1. The third seat, well, it's open, no restrictions. There are 6 choices for that seat. Whoever's seated there, the other part of the couple has to be there. And continuing this pattern gives us that answer. Now we could have also looked at this and said, okay, let's think about the couples. We have 4 couples, so 4 times 3 times 2 times 1, or in other words, 4 factorial will organize the couples. So there's 4 factorial ways of moving the couples around. Now each couple has 2 ways to be seated, right? So the first couple has 2 ways, so if you multiply by 2, that gets both ways that they could be seated. The second couple, third couple, and the fourth couple. So I need to take this 4 factorial and multiply by 2 to the 4th, because there are 4 different couples, and that will count all of the flips between the couples. So personally I like the top way best, but the second way is also another method to solve the problem. A box contains these objects. How many different samples of 30 can be selected if part A says at least 3 are red? So 3 red says 3, 4, 5, all the way up to 30. Well, notice red stops at 23, so it really stops at 23. And these are all the different cases for red. Now, personally, it's way too many to write down, so I look at what I don't want. I don't want 0, 1, or 2 red. So total minus what I don't want is the easiest way to count this. If you count up the number of balls, there are 115. Choose 30. That's total. Now minus what I don't want, 0 red. That means from the remaining, there are 92 of them. I need 30. Or 1 red. Or 2 reds. Part B says, how many ways can we get at least 28 yellow? Well, looking at the list, there's only 22 yellow to start with. Well, I have no way to get 28, 29, or 30 yellow, so the answer is 0. Part C says, at most 27 are blue. Well, at most means 27 or less, so this is 0, 1, 2, all the way up to 27. For this one here, I don't want 28, 29, or 30. So total minus what I don't want. There's my total. Now I don't want 28 blue, so of the 30 blue, pick 28. Of the remaining, well, count the things that are not blue, there are 85 of those. Pick 2. That's 28 blue, now we do 29. And then we do 30 blue.